3, we will look at the relationship between matter and energy. The first thing we'll look at is the law of conservation of mass, and this states that matter will neither be created nor destroyed during a chemical reaction. It can only be changed from one form to another. You can change mass to energy, energy to mass, different types of energy, but there is no new matter being created. It is always going to exist in some form. Now, in a nuclear reaction, you can get significant changes in mass, but for standard chemical reactions, no new matter created or destroyed. So, for a chemical reaction, you might see a change in mass, but it's very minute. So, relative to the entire mass of it, it's insignificant. We will hold the premise that during a physical or chemical change, the total amount of matter must remain constant. So the mass will essentially remain constant. An illustration of this, suppose that we take that butane lighter that we looked at earlier and we burn 58 grams of fuel from that lighter. Now, in order to burn that much butane, we will need 208 grams of oxygen, and that reaction will form 176 grams of carbon dioxide gas and 90 grams of water vapor, so water as a gas. Now, if we look at that reaction, we can see that we have butane plus oxygen yields, okay, so the arrow means forms or yields, carbon dioxide plus water. We said we had 58 grams of butane and 208 grams of oxygen, so the mass that we had to start with was 266 grams of matter. If we look at the products that are produced, the carbon dioxide and the water vapor, we had 176 grams of carbon dioxide, we had 90 grams of water vapor. When we add those two together, we see that we still have the 266 grams that we started with. None of the matter was destroyed, we didn't create any new matter, it just got changed from one form to another. Now, in addition to the matter that is being changed in a chemical reaction, we want to look at the idea of the energy involved in a reaction. Energy becomes very important to us in chemical reactions. So be aware that energy is a major component of the universe, and it is also defined as the capacity to do work. If something has energy, it has the ability or capacity to accomplish some work, where work is defined as the result of force acting over a distance. So, and it's also relative to the mass of the object. Now, the behavior of matter is actually driven by energy. It's driven by that capacity to do work, or the work that has been done. So understanding energy and different types of energy becomes critical to understanding chemical reactions. So this leads to the law of conservation of energy. And just like the law of conservation of mass, energy is going to be conserved. Energy will neither be created nor destroyed. It will only be changed from one form to another. Energy can also be transferred from one object to another. So we can have a transfer of energy from, for instance, if you drop a book, transferring the energy from the motion of the book to the surroundings, to the floor, wherever it interacts. And we can't create energy from nowhere, and it doesn't vanish into nothing. So, for example, if that book is going to be dropped, it had to be lifted in the first place. Work had to be done in order to transfer energy to the book that then was released upon the book dropping. Now, there are different forms of energy, but the total energy of a sample of matter is just the sum of its kinetic energy, which is the energy associated with motion, plus its potential energy, which is the energy associated with position or with composition. So kinetic energy plus potential energy equals total energy. Now, of those kinds of energy, there's electrical energy, which is the energy associated with the flow of an electrical charge of electrons through something. We'll be looking at electrons a lot later. There is thermal energy, which is the energy associated with the motion of atoms and molecules in matter, random motion. So remember we said that in a solid, the molecules are vibrating around a fixed point. Liquids and gases, there's the motion of the molecules. This can translate to thermal energy, and thermal energy becomes very important to the states of matter. And then we have chemical energy, which is a form of potential energy which is associated with the position of particles that make up our chemical system, that make up our reaction or our equation. Now, when we talk about energy, remember that we're using the SI system of units. So the SI unit for energy is the joule, okay, Joule, and it's abbreviated capital J. It's named after the English scientist James Joule, who was the first to demonstrate that energy could be converted from one type to another, and that there was a conservation of energy, so that energy was not being created or destroyed. Now, there's another unit of energy in the English system that you're probably more familiar with, and that's the calorie. Okay. Now, this actually may not be the calorie that you're as familiar with, so we'll see that down here in the next step, but a calorie, lowercase cal, is the amount of energy that it takes to raise the temperature of 1 gram of water. Remember, 1 gram is about the mass of one paperclip by 1 degree Celsius. So a calorie is a little bit larger than a joule. There are actually a little more than 4 joules for every 1 calorie. Now, the related energy unit that you're probably more familiar with is the nutritional calorie, or calorie always spelled with a capital C. So if you look on your food packages, food labels, you'll see that the word calorie is, or at least should be, always written with a capital C. And when you see calorie written with a capital C, that is a kilocalorie. It's equivalent to 1,000 of these calories up here with the lowercase c. Okay? So when you are drinking a soda and it says that it contains 260 calories with the capital C, it's actually 260,000 of these calories up here. Okay? There's also a kilowatt hour, so you may be familiar with that one in terms of your electric bill or power. 1 kilojoule per second times 3,600 seconds in an hour. Okay. And just to kind of relate that, kilowatt hours are what residential electricity is measured in. The average cost of that is about 12 cents per kilowatt hour. So you could do the math and you could figure out, if it's that much per kilowatt hour, how much would it be per kilojoule second or something like that. That's certainly an example we could look at. All right, so in order to be able to do energy calculations, in order to be able to do our dimensional analysis, we need to know what the energy conversion factors will be, what the equivalences are. So remember we said anytime we have things that are equivalent, we can divide one by the other. It's essentially equal to 1, and we can use that to multiply things to change units. So, as we said, a calorie is a little bit bigger than a joule. There's a little more than 4 joules, 4.184 joules in 1 calorie with a small c. 1 calorie with a capital C, 1 kilocalorie, is 1,000 calories with a small c. And 1 kilowatt hour is 3.6 times 10 to the 6th joules. So we'll need to keep those in mind as we look through the next few examples and as you do your homework. All right, so here's one example. We have a candy bar that says it has 225 calories in it. So it's calories with a capital C, it's nutritional energy. How many joules of energy are in that candy bar? All right, so we know that we have 225 calories. We're trying to find joules, so we need to set up our solution now. We're trying to start with kilocalories, and we want to convert that eventually into joules. I don't have anything that let me do it directly, but I did have a relationship between these calories and calorie with a small c, and I also had a relationship between this calorie and the joule. So in this step, if I use this equivalence, 1,000 calories to 1 kilocalorie, that allows this calorie to cancel out with this calorie, leaves me with these. Now these, if I use this equivalence, 4.184 joules, divided by 1 calorie with a small c, now these cancel out, and it leaves me with just the joules. Okay, so here's my two relationships. Those are both from table 3.2 in the book and the one that was in the previous slide. And here's how I set up my solution. I start with my calories with a capital C. I divide by this, multiply by calorie with a small c, so times 1,000. Okay, now I use the next step, multiply by 4.184. Now calories with a small c cancel out. The only unit left is joules, which is what I want. So I end up with 9.41 times 10 to the 5th joules. Okay, you should try setting this problem up without looking at the slide on your own and try doing the math. Make sure you can replicate that. You might try it with a different number of calories and see what you get, and see if it makes sense. Do you end up with more or less joules if you start with more or less calories here? So for example, you might try something that contains let's say 450 calories. That's a typical frozen entree. So try 450 calories, see how many joules you end up with, and we can look at that on Friday in class. All right, now we talked about the different types of energy, potential and kinetic energy. Now, potential energy is the energy of position, and it's the potential to do work. So for example, if we have a 10 kilogram weight and we lift it off the ground and move it to the top of this building, it has a high potential energy. It has energy stored in it based on its position. It will have a tendency, if we put it like this on the edge of the building, to fall toward the ground and lower that potential energy. Okay, so it falls off. When it strikes, some of its energy is actually being translated into heat energy. The pavement will actually take in some of that energy that is being transferred from high potential to low potential, more unstable to more stable, and it translates into the surroundings. Now, why is that important to chemistry? We're not really dropping weights off of buildings. Well, it's because if we have a system that has high potential energy, a high amount of energy stored in it, it will have a tendency to change itself in a way that lowers that potential energy. A lower potential energy position is a more stable position. Okay, so anything with high potential energy tends to be unstable. Things like trinitrotoluene, also known to us as TNT. TNT has a very high potential energy. It's got a lot of potential energy stored in that system. Okay? So that's why if we can kind of just push it over the edge a little, just like that weight on the edge of the building, if we push it over the edge, it undergoes a rapid chemical change. It rapidly converts potential energy into heat energy, light energy, sound waves. Okay? So that is why TNT is explosive, because just one little push and it very rapidly undergoes a chemical change to a more stable position. Now, that is going to relate to chemical reactions and spontaneous reactions, or reactions that require energy in order to happen. We'll be looking at this a lot in coming chapters, but just to introduce these terms right now. If you've not heard of these before, you can have two different types of reaction energies going on in a chemical reaction. If you have a reaction in which energy is being released from the reaction, which you will probably usually translate as heat energy. It does not have to be heat, but that is the most usual type of energy that we see. That is known as an exothermic reaction. So the TNT that we just talked about, If we look at it in this diagram here, A, if we say here's energy increasing over the system, the reactants started up here at some high energy, and then the reaction occurs, energy was released. Our products have a lower potential energy, a lower amount of energy stored. Okay, this energy that's released usually comes off in the form of heat or light, something like that. Okay, that's an exothermic reaction. Heat packs, if you've ever used a heat pack, that's an exothermic reaction. Now, on the opposite end of things, endothermic reactions. This is where energy is being absorbed by a system. So our reactants are starting down here somewhere. They're soaking up energy. Again, it can be in different forms, but usually in the form of heat. And it ends up here at a higher potential energy. Energy is being absorbed. Okay, now if you think about this, how would we sense these systems? Now, an exothermic reaction, you probably already have a pretty good feel for that. If I use a chemical hot pack, what am I going to feel? I'm going to feel heat. I'm going to feel the energy being released by that system. Conversely, if I have an endothermic reaction, if I have a cold pack, energy is going to be absorbed by that system. I may be part of the surroundings of that system, and it may be absorbing my energy, so I will feel colder. It will feel cold to me as it absorbs my energy. Okay? So exothermic, giving off energy, endothermic, absorbing energy. And I want to issue just a little challenge to you. What I'd like you to do is, if you have it on hand, get some household vinegar and a little bit of baking soda. And this is the classic 4th grade volcano. And what I want you to do is get a glass or a cup, something that you can hold in your hand and feel, put a little baking soda in there, and then add a little vinegar to it. Now, you want enough so that you've got probably, half a cup to a cup of vinegar in there total. Just be aware, remember it does foam up, so you may want to do this over the sink so it doesn't make a big mess. But what I want you to do is carry out that reaction and then decide, is that an exothermic reaction or an endothermic reaction? And then we'll talk about that on Friday. All right, so that concludes part 3, and the next part, part 4, will wrap up chapter 3.